Okay, perfect. So hello everybody. I'm very pleased to be with you today for this webinar about automation of Actran Simulations using the Application Programming Interface. So as indicated, my name is Bernard van Anterpen and I am managing the qualification and validation process at Freefield Technologies, or FFT in short. FFT is an MSc company and is the editor of the Actran software. So today's webinar is the 7th of this 2012 acoustic series. During session 1, we have discussed the acoustic radiation. Session 2 was about strongly coupled vibro-acoustics. Aero-acoustic simulations was the topic of session 3. The simulation of noise absorption within porous materials was covered in session 4, and the modeling of intake or exhaust systems was presented in session 5. Session 6 presented the new Actran 13 release and its major features. Today, we will focus on automation of Actran computations through the usage of our Application Programming Interface, or API in short. For your information, the recordings of those previous sessions are available on the MSc software website. So, the points we have on the agenda today are the following. First, I will introduce you on the concept of the Application Programming Interface. Second, we will look at the content of the API within our graphical user interfaces. This includes the type of functions and objects that are accessible, but also how to retrieve session files within the graphical user interface. Third, we will review the use of this API through scripts and sessions for different purposes, such as saving an actual state of the graphical user interface, relaunching a part of a post-processing step, automating your Actran simulations, or performing parametric studies, for instance. I will then guide you through Actran VI, the graphical user interface of Actran, during a live demo. And then we will finally conclude this presentation in one slide, and then we'll have our Q&A session. As introduced during the previous webinar sessions, the Actran software is divided in different modules. Most modules presented here are computational modules. They are containing the different features necessary to simulate particular physics or excitations. All those modules are encapsulated within Actran VI, the pre- and post-processing tool to manage any type of Actran simulations, despite the required features to run the simulation. It is in this module of Actran that the Application Programming Interface is accessible. It is useful for any type of Actran users using any type of other module. Before starting the review of the API, I will briefly introduce you to Actran VI and utilities. The Actran VI module is the dedicated pre- and post-processing tool for Actran application. The graphical user interface allows to perform various actions, from the import and export of Actran analysis or meshes to the creation and addition of Actran analysis. It also contains small meshing tools, particular visualization of acoustic components and boundary conditions, or a tool for predicting the projection quality of incongruent meshes. Actran VI is also dedicated for visualizing acoustic or structural results obtained by Actran or any other tool. It supports various result types that can be visualized in different visualization modules as shown below. Figures and animations of your Actran results can also be requested. The PLTViewer and the WaterfallViewer are dedicated tools for post-processing frequency response functions, or FRF in short. These are accessible from Actran VI and are part of the Actran VI module. Both tools can import different result formats, including external data provided by other tools, such as MATLAB or Excel, to combine different results into a common visualization. It also contains various operators or functions particular to acoustic analysis, and allows the user to create its own set of functions. This data can either be visualized within the PLTViewer, which allows to plot curves on multiple figures, or within the WaterfallViewer for visualizing a waterfall diagram when output varies following two indicators, for instance, frequency and 1 per minute. Before starting the review of the different key features of the Application Programming Interface, let's first review what an API actually is. An API is an interface or language provided by a software to allow communication with other softwares or users. It usually includes the specification of the different actions that can be taken, the structure of data that can be accessed, among others. The API limits what can be done and what can be requested. The main benefit of an API lies in the fact that everybody can access this language and create applications based on this, without having to rewrite all possible functions by yourself. In practice, for Actran users, the usage of an API could allow them to control and operate the different actions he can perform manually within the graphical user interface. It could also allow them to access internally data structures easily, mainly for post-processing steps. As indicated in the previous slide, Actran VI and its related and utilities provide their own native commands API based on a Python language. The content of this API in Actran VI is sensitively identical to all manual operations the user can perform within the graphical user interface. As all performed actions in the graphical user interface can be translated into a particular command, all these operations are thus recorded into a session file within the graphical user interface, as you can see below. The syntax used within the API is rather easy to understand, as similar concepts and syntax are used with respect to the Actran input file. As all performed actions in the graphical user interface are translated into an API command, these can be retrieved when using the graphical user interface. Both Actran VI and the PLTViewer contain an interactive console which registers the different performed operations. This console can be used to perform operations interactively, retrieve some help on the API or on particular objects of the graphical user interface. But all these operations are also automatically stored into a session file without the need to specify this. If you're closing an application without saving the last state, you can always retrieve the latest produced session file in the described folder, depending on your operating system. As indicated, an API provides a full set of functions and object types which can be used. The complete list of functions and object types are documented within the Actran VI User's Guide. But we will review in this section a basic list of these to explain the philosophy of the API content. The type of objects that are accessible within Actran VI is very similar to the type of concepts present in an Actran computation. Among others, the API can access materials, meshes or domains, components, boundary conditions, analysis, tables, or visualization and result containers for post-processing operation. For modifying an object, one particular need is to be able to point towards this object. These are directly referenced if created during the session, manually or within the Actran console. As shown on the image below, an automatic name is provided which will allow the API to access this object later on. When importing an existing analysis, for instance, we do not create a reference to a particular object at the import. The different GET functions in the API can, however, retrieve a particular object. For instance, a component could be retrieved by providing its identification number. Within the graphical user interface, a last and easy way to retrieve the reference to the object consists in dragging the object within the interactive console directly. Actran VI contains a very extended list of functions for manipulating all types of objects. These can usually be divided in 5 types of operations. The operations consisting in the creation of an object, simultaneously the object and its reference which is described in the API command are generated. A particular command exists for each type of object such as components and materials. In the presented case, we are obviously adding a component and the name is then changing. The operations consisting in retrieving an object that has not been referenced because it has been imported, for instance. The operations consisting in modifying an attribute of an object is supported by the setProp function and can be applied to all types of objects. Please note that multiple attribute changes can be performed within the same API command using this function. The add function allows to add an object underneath another object, typically for referencing a domain within a component or boundary condition. Finally, objects can also be removed from the internal database. Besides these basic functions, many other advanced functions are also available. For instance, functions to close the graphical user interface, import or export Actran input files or meshes, perform some meshing operations, modify the interpolation order of a particular mesh, create local microphones, exporting an image or animation of the render window, among others. All these available functions are listed within the Actran VI User's Guide. For post-processing frequency response functions within the PLTViewer, the number of objects that can be accessed and functions within the API are much more restrained. When importing a result file, the selected results are imported and become an object that can be referenced. To plot curves of various results, functions have to be created and defined. These can then be plotted to curves and on figures. These three objects and their properties can be created and edited. Three main operation types can be performed. These consist in the creation, addition, and removal of the different objects. Many additional functions are available, such as the import of result files, the export of figures as text files or images, or the merge and revert operations of imported data structures. An additional complexity for post-processing frequency response functions consists in retrieving the different outputs contained in imported result files. These are directly used in the creation of the functions and need to be easily accessed. In the API, a particular output from an Actran result file can be retrieved by specifying the result file, the object type and identifier, the field and load case to be selected. In this example, the mean square pressure field of the first acoustic component from the first result file is selected. To ease the post-processing, a particular need consists in iterating on a series of objects or getting the content of a particular container. This is needed to iterate on the different load cases or microphones, for instance. By selecting an object type, the user gets access to the subcontainers directly. If needed, the content of a particular object can be obtained directly by using the IDS keyword. On the three shown examples, the list of points, the list of fields, and the list of load cases will be provided to the user. Due to the extensive amount of functions, object types, and properties, it is important to get access to a complete help. As indicated previously, the complete list of functions, including their arguments and syntax, is provided within the Actran VI User's Guide. An interactive help is also provided within the console of Actran VI. The help function provides the help for a required function. In the shown example, all functions containing the name BC are listed, including their syntax, required arguments, and default values for the different arguments. The help on an API object provides the complete list of properties of the object type that can be edited. For each property, a default quantity and a quantity type is specified. And as indicated previously, the reference of an existing object can easily be retrieved by dragging the object directly into the interactive console. Okay, let's now review what can be done with the available API. First, the most basic application for the API consists in saving and loading the current state of an Actran project within the Graphical User Interface. Secondly, templates for typical analysis using the same type of components, boundary conditions, or materials can be saved for further usage. Third, pre- and post-processing steps can be edited to avoid manual operations. Fourth, pre- and post-processing steps and the computational step can be automized in one computational step. Finally, the API can be used to create additional user functions. The RADACT utility that is used to produce and post-process acoustic radiation simulations is a typical example of such advanced applications. Parametric studies are also typical examples of such advanced functions. So, the current state of an Actran project within the Graphical User Interface can be saved at any time by saving the session file containing all previously performed operations. As indicated previously, an identical file is already created at the startup of the Graphical User Interface. To replay a session, this is simply performed either directly within the Graphical User Interface and selecting Load Session, or in batch mode using a command line. When loading directly the Graphical User Interface, the user can either choose to import the previously imported files, supporting the mesh or result files, or to interactively import these files. It is already a good example of how to use templates actually. When using the batch mode, the user can choose to work in non-graphical mode, allowing to perform pre- and post-processing operations directly on a cluster, for instance. The usages of sessions or scripts can ease many different pre- and post-processing operations by reducing the number of manual operations. A typical example consists in modifying some parameters in an existing session file to produce a different input file, without having to perform all other operations manually. On the shown example, the mesh file supporting the computation can be easily modified by just changing the file name within the session file. During post-processing, many identical operations usually need to be performed when comparing different but similar result files. By copying a typical section of the post-processing operations, we can easily produce all the different results in one or multiple figures without having to perform manual operations. This can also be reused afterwards for new result files, for instance. If the pre- and post-processing steps of a typical analysis are already optimized, one last optimization usually consists in running the complete simulation into one step. This can be usually performed in two ways. As all sessions can be launched in batch mode without the graphical support, the user just runs the different commands either manually or in batch. This can be performed without graphical support directly on a cluster environment, for instance. But the three different steps can also be merged into a single session file by using the run function to directly obtain this solution. A further usage would obviously consist in generating iterations between the different steps for optimization, for instance. So let's now discuss about a typical example of advanced usage of the API, Parametric Studies. Parametric Studies consist in assessing the impact of certain parameters on the design. Parametric Studies consist in choosing the parameters for evaluation, define the parameter range, specify the design constraints, and analyze the results of each parameter variation. In practice, such parametric studies require to launch several computations for which the parameter has to be modified. The usage of the API is a key feature for automating these required operations. In practice, the type of parameters is usually of two kinds. Either external inputs, such as the dimension of the problem through the mesh file, structural results for performing acoustic radiation, or CFD data, for instance. In some cases, only a few amounts or even no changes need to be applied on the Actran input file for producing all type of results. If the external input heavily influences the generation of the input file, scripting will then be required. The other type of parameter can be model parameters, such as component or material properties, boundary conditions, and so on. Scripting will be required for such parameters as a new Actran input file will be mandatory. The case study we will consider now is a parametric study of a treated ski cabin. The parameters of interest are linked to the porous treatments that are applied through the seats and carpet. In practice, the two parameters we wish to modify are the porosity and flow resistivity of the foams. We will assess their influence on the microphones placed within the cabin directly. In this case study, we will automate both model generation, computation, and post-processing of the results in one main master script. This script will first read the range values of the different parameters provided by the user and the template for creating the Actran model from scratch. The generation and computation of the Actran files will be performed by the master script, which will manage the different outputs. The global post-process will be performed through a waterfall diagram. The template of the analysis provided by the original session file without modifying the parameters will be slightly modified in order to indicate the parameters of the study and the modified output files. By modifying the ranges of the parameters and modifying the template, the master scripts could actually be reused for any similar case study in the future. The post-processing step of the master script is also automated. During this step, all produced result files with the different parameters are read and concatenated into a waterfall diagram automatically. The provided script can then easily be modified to perform parametric studies on different parameters using a different template. The post-processing step is obviously launched at the end of all computations. And now we can see a typical example of a parametric study obtained with Actran. In this case, we observe that the minimal sound pressure level at the microphone is obtained using a foam having a flow resistivity of 80,000 and a porosity factor of 0.72. The waterfall utility also enables to visualize curves for particular fixed quantities of flow, resistivity, and porosity, in the case where one of the two parameters could finally not be modified, for instance. Okay, I will now guide you through the graphical user interface during a live demo. In this demo, we will treat a model that is very similar to the model involved in the previous webinar about exhaust noise problems. The objective of the demo is to compute the pipe noise of a muffler submitted to an engine pulse excitation. The input requirement is a finite element mesh containing the different domains, 3D domains for the interior air and 2D domains for the duct mode components that we will use at the inlet and outlet. The main output we will consider is the transmission loss of the muffler that is defined as the ratio between the incident and transmitted power. In order to highlight the different advantages of using the API, two different models will be treated using the same session file. Both pre- and post-processing will be automated. So, I will now directly go for this demo within Actran VI. So, this is here Actran VI, as you can see. So, Actran VI is the pre- and post-processing utility that we will use to create the session file and the actual input file. So in order to start, the first thing I will do is to import the first mesh that I have presented. So I am importing here this mesh, so we can see that this is a part of an exhaust system. It is actually a muffler, and I have, as indicated, two surfaces for supporting the modal duct components and the interior acoustics. So what we will do at first is from scratch start a new Actran analysis. So I will produce now a new Actran analysis here. I will specify the frequencies of interest. So here we are interested into a frequency range getting from 10 to 750 Hertz with a step of 10 Hertz. I will also automatically create all the domains supporting the different element sets. And I will directly create an acoustic component for supporting the interior fluid. I will also add a fluid material for describing this fluid. So for now on, let's have a look at what I did. So I created some domains, a material, an analysis, and a component. Actually, every operation that I did so far is saved into the session file in here. So into the console. And you see that every operation that I did manually was translated into an API command. So what I can do from now on is to export a session if, for instance, I need to stop my work right now. So I will call it temporary session.set. And if I want to now, for instance, clear everything and get the last state, what I can do is just replay my session from scratch. And you see that when replaying the session, it has recreated all the domains, the materials, the different components. So now I can move on and create my different modal duct components. So here what I will do is at first create the inlet. So I am assigning the domain and the material. I'm computing the geometrical parameters and the modal duct system of axes. And I will now create two modes. The first mode, which is propagating mode, so it is representing the engine pulse excitation. So I will allow all the modes from 0 to 750 Hertz. In this case, it will only be the plane wave. And the other mode will be a free mode for ensuring a non-reflective boundary condition at the inlet. So I am also specifying the range at the same time. You see that any type of operation that I am actually performing here is translated into the session file. I can now also create this for the outlet. So here I am pointing towards the outlet. I am assigning the same material, computing the geometrical parameters that are slightly different in this case. And now I will also specify a non-reflective boundary condition at the outlet in order to allow an infinite duct. Okay, so now the only thing I still need to create is the mem solver that we have here, and to add an output of the FRF. So here I will use the auto keyword. So basically we will have the same name as the input file. And now I can export this as test mesh1.edat as an input file. What I can also do is export in the session to temporary session.ses and to have a look at what happened over there. So what we have now here is a temporary session. So this is in Python format. And what we see is all the operations that we have actually performed. So basically the first part here was before I cleaned up everything, so I can suppress this part here. And what would be interesting is to actually have this to perform the same type of analysis for different but similar cases. For instance, for Mesh 2. I have already done this into this session. I have performed some small changes that I will show right now. The first change is the fact that I am actually pointing towards Mesh 2 instead of Mesh 1. The other change is basically almost nothing. The main change I am applying is that the geometrical parameters of the modal duct obviously depends on the mesh type. So what I have done is, instead of describing explicitly the different system of axes and radius, for instance, of the modal basis, what I have done is I have used the API functions that are doing exactly the same as the three different buttons, so that are computing the center of the modal duct components, for instance, or to retrieve the radius of the modal duct. I have performed that for circular duct 1, so for the inlet and for the outlet, and I have just commented the writing of the analysis here. So let's just play this session here. So I will first clear all trees again, and then I will load my second session here, so session VI. And so this one will import the mesh that corresponds to the second model, will create me my material, my analysis, and so on. And what we can do is just make a small check to see that the geometry of the modal ducts and components are correctly hand computed. So that means that right now I have a session file here, so we see that everything is fine. Right now I have a session file that can be used for any similar meshes to produce automatically an Actran input file without having to perform all these manual operations automatically. So this is a good example of automating the pre-processing of Actran. So let's now see how we can do that for the different output files. So here you see that I have already computed the different result files. So what I will do first is to open my result file within the PLTViewer in order to have access to the outputs. So what I will do is automatically compute the transmission loss of the first model. So what I do is that I'm creating a new function, and I'm drag and dropping the incident and the transmitted power here. And then I am plotting the new function. So here again, I could save this session here by calling it temporary session.ses. And again, I can just replay automatically my session over and over and over. Now, if I want to visualize my two outputs from my two different meshes into one session file, what I can do is just make a small addition in here, so that in case of those two PLT files are changing all the time, I can just replay in the session without changing anything. So what I can do is just copy paste this whole part where we are importing the file and we are creating the curves. The only thing that I will do is that I will change the name of my PLT file. So here I will write down West Mesh 2. And what I will do in order to avoid to have a new figure is that I will just suppress this line over here. And what I'll do now is that I'll launch here directly in the same folder the command of the command line to launch the PLTViewer in batch mode. So if I execute this session, what I will get is the two produced curves on the same figure. Now what we could also do is, for instance, save this as an image. So here that's what I am performing, and you see that I could also copy paste this line over here and add this directly within my session file in order to produce an image directly at the next time that I am relaunching this session. And what we will perform right now is the same execution but in non-graphical mode. So before that, what I'll do is that I'll suppress the image that was produced by Actran, and I will now launch the same command line, so Actran pi minus PLTViewer for the PLTViewer, minus X my session file, and then minus N for activating the non-graphical mode. And this will produce me automatically an image that will appear in here that is representing the same image as we had before. Okay, so this was our live demo. So let's now conclude. During this webinar, the concepts of the API and this particular language have been introduced. A small introduction to the philosophy of the API syntax has been shown. The different usages of the Actran API have been shown, such as saving an actual state of the graphical user interface, relaunching a part of the pre- or post-processing step, automating your Actran simulations, or performing parametric studies. As such, it enables the integration of the acoustic simulations with Actran within the design cycle of engineering products. The main features of the API have also been introduced, and we have reviewed some of them during a live demo. Thank you very much for your attention. I think that we can now start our Q&A session.